And so you should all be seeing my PowerPoint slide. Welcome to CineGrid Community Forum in September. And these community forum have been a monthly online session at the intersection of media and AI. We have been running these since February of 2021. The first two sessions last spring looked at the open science cloud called Nautilus, which is a federated Kubernetes managed science cloud through more than 20 institutions in California and elsewhere. We had a really wonderful talk from Professor Angus Forbes from the University of California, Santa Cruz, about what his team is doing in the creative coding lab, dealing with AI and creativity, including the use of generative AI to create images. We had a very stimulating presentation from our colleague, Professor Kunitake Kaneko at Keio University in Japan, who talked about his idea for the graph system for next generation networks and the creation of metadata that can be analyzed using graph analysis. In June, apparently I pressed the wrong button. In June, our longtime colleagues, Jason Lee from the University of Hawaii and Luke Renenbo from the University of Illinois in Chicago gave us a really stimulating presentation about their third generation SAGE environment for remote collaboration and how they anticipate using AI to support remote collaboration. In July, we had a really deep dive into the state of the art of electron microscopy and both the imaging technology, the computer architectures, and the AI workflow needed to exploit the capabilities of modern electron microscopy, especially as it is applied to brain anatomy. And then last month in August, our friend Alvy Ray Smith gave us a presentation about his new book, A Biography of the Pixel. All these sessions were recorded and are currently accessible on the CineGrid Forum archives, which is essentially a CineGrid channel on YouTube. We have two more presentations coming up in the fall, in October 19th and 20th. We'll look again at remote collaboration, distance learning, and hybrid workplaces with our longtime CineGrid collaborator, Greg Harper, who is going to really concentrate on the human factors of remote collaboration and how modern AV technology can be used to ameliorate the human factors obstacles to effective remote collaboration. Those of you who don't know him, Jeff is a fountain of knowledge about audio-video technology. And in December, we'll have a presentation from Brian Hansen, a researcher at University of California, Santa Cruz, on AI-generated sound effects for gaming and movies. So we hope that everybody can make those sessions as well. We have a very simple agenda today. I'm doing the introduction right now, and we're going to have a talk on how artificial intelligence is transforming moving picture restoration. We will have a Q&A after the presentation. And of course, we're always looking for next generation projects. It is my pleasure to, pardon me, lost my place on my computer. It's my pleasure to introduce Algosoft Technologies in this month's CineGrid Community Forum. Algosoft was founded in 2006 by CEO Dr. Inna Koslov and CTO Dr. Alec Petukhov. And please excuse me if I don't pronounce your names correctly. Prior to founding Algosoft, Ina Koslov was the head of the signal processing department at Technion University, and then head of the computer science department at Holon Institute of Technology, both in Israel. In parallel with his Algosoft activities, Alec Petukhov is also an associate professor of mathematics at the University of Georgia. We're also joined today by Mike Inchalik, a moving image restoration technology, operations, and strategy consultant to Algosoft. Mike has been a pioneer in image processing technologies for film, television, and consumer electronics over the years at companies such as Kodak, Lowry Digital Images, DTS Digital Images, Reliance MediaWorks, and PurePix. Today's presentation will focus on Algosoft's techniques for applying AI to film restoration and image enhancement. Mike and Alex will introduce Algosoft, their suite of software tools, and specifically how they are improving the way complex film restoration can be done with greater automation at lower cost. They will present examples which highlight several of the algorithms they've developed and demonstrate their results using before and after film sequences. And during Q&A, they'll be joined by Ina. Please hold your questions until the Q&A session after the presentation, or share them via Zoom chat during the session. Please note that what you see on your screen may vary. Algosoft typically starts with high-resolution film scans, which are processed with very high mathematical precision and output as cinema quality image sequences. The examples being presented today are compressed clips playing on a laptop through PowerPoint, then screen shared in Zoom using Zoom's virtual frame buffer, and streamed to each of you using Zoom's adaptive bitrate codecs that automatically adjusts levels of compression and frame rates to fit the available bandwidth at each client. So no guarantee exactly what you're going to see, but please be assured that what Algosoft started with was extremely high quality. And so with no further ado, I'd like to turn this over to Mike, and we're ready to go. And so.
Beautiful. Thank you so much, Lauren, and it's a pleasure to greet you all. Let's just make sure that we are all seeing the same thing. Can you see my
yes. Yeah,
slide? Beautiful. All right. So looking at this kind of shortly, I'm the setup guy. I'm going to try and provide context to what you're going to hear in more depth about artificial intelligence, neural networks, and topologies and algorithms. But to put this into the right kind of perspective to understand the challenge of moving picture restoration and how it's fundamentally different than most of the things we deal with. What we'll try and discuss today is initially those challenges facing restoration of the world's assets and some of the basics, some of the terminology we use. Then Alex will be on to talk about the technical challenge of detecting the problematic image areas that need to be addressed, how to replace them, and what can be done with overall image quality as three different slices of technical detail. And we'll conclude with looking forward and what's next. So let's dig in first to the environment. What's unique about restoration is that unlike most imaging applications we deal with today, where the imagery comes from higher and higher quality sensors and capture devices feeding higher and higher quality displays, is a situation in the restoration world where the media, represented by the blue line you see here, is actually degrading and losing quality over time. That's a factor, of course, of all analog imaging and storage, but especially with the age of many of the assets we're dealing with. So essentially, the picture information remaining on that media is falling off every year at the same time as the expectations for the quality we want to extract from it increase. And if we look at that kind of in a little more detail, The media quality itself erodes from aging and degradation as dyes fade, etc., but also duplication to keep the elements available to us as we handle them, as we print from them, as we try and keep them subtle. We make duplicates which lose detail. And then finally, we have the handling and use themselves. All of those things take quality away from those original elements. On the flip side, it's the consumer spending that justifies or has justified most restoration projects to date. If you think back to your own ownership of movies, for example, this could be VHS releases of a movie that were then resold when DVD was made available, when optical disc, laser disc was available, then Blu-ray. Those kinds of expectations and the purchase of that media is what has driven restoration in the past. And that's been driven by consumer electronics, which has this never-ending and very positive drive to get us to buy better and better quality devices. It's also echoed in digital cinema. Sometimes these media are re-released in cinema, and the cinemas of today compared to, say, the carbon arc theaters of nearly 100 years ago display far more resolution, far more dynamic range, far wider gamut, etc. And if we look at those consumer expectations, I won't harp on this issue, but the reality is we have a continuing stream of improvements that add resolution, color, gamut, frame range, and dynamic range, as well as brightness to these things. And in fact, as most of you probably know, the illusion on the eye of seeing motion by flashing still images is greatly affected by brightness. The brighter the image is, the higher frame rate you have to use to fool the eye. So as we continue to evolve our viewing environments, we can expect to continue to progress along this line. So the technical challenge in restoration is closing this gap between the falling quality that's inherent in the elements and the continually increasing demand for quality from the viewer, because they're looking at it on bigger, brighter, more resolute, wider gamut, faster frame rate kinds of devices. But that's only part of the issue. The other issue when it comes to restoration is that restoration, much like so much in the world, follows the Pareto principle. Right? The Pareto principle says that 80% of the value in most any endeavor, most any market, comes from 20% of the activities. And that, by the way, is what's called fractal or recursive, meaning that 80% of that 80% comes from 20% of those 20%, meaning 4% of your assets have 64% of your value. Same thing as why 4% of the population has 64% of the wealth. You know, it is a common thing that pervades everything. What does all that mean here? It means that that the mass of media out there to be saved has much lower quality, much lower potential financial return associated with the restoration. And the restorations that have been done to date, those restorations have been focused on the absolute blockbusters, those titles that can get a clear and positive return. But they are just the tip of the iceberg, just the tip of this pyramid. And our challenge, if we want to save our cultural assets, our scientific and other knowledge embodied in video and film assets, is to get the cost of restoration down so we can afford to deal with the titles at the bottom of this pyramid. So we have to drive our technology to the point that it can operate at 5 or 10% at most of the kind of budgets we've been used to working on. And that requires automation and collaboration and tools with power we haven't seen before. And that's only part of the problem, because it's also true that when we're trying to restore old media, it's not just about automation. It's not just about price point, but we have to preserve historical accuracy. We have to preserve the creative intent associated with these titles, and that requires human intervention and intelligence, which to date can't be embodied in the algorithms themselves. So the devil is in the details around how we get the price point and the efficiency of these processes to where they need to get. So let's talk about restoration more broadly and set some terminology, as well as discuss where the problem areas are, so we can loop back with Alex and talk about what progress has been made. Taking just aging as an example, and I've had a distinctly filmic approach as I've been talking here. So the bullets you see at the top, dye, fade, color breathing, and flicker, which really have to do with fading, differential fading around the lapse of a reel of film, shrinkage, warping, mold, brittleness, and crazing. Those are filmic ways in which film media falls apart, but there's a similar set of challenges that affect magnetic media. In fact, typically they happen faster and are more catastrophic. That's magnetic signal loss and magnetic print through and bit rot and all the other kinds of things we see. And I'm not even touching on the challenges of how do you actually digitize things with legacy devices that don't exist anymore. But these artifacts from aging, there's a wide range of these artifacts from aging, and it's not the only way, as we've discussed, in which the imagery loses quality over time, right? The problems we see in the surviving imagery in Elements can come from the original photography and the post-production. There's nothing about the processing of that original film that had to be perfect. The film itself wasn't always perfect. We have aging, then we have the duplication we've talked about, then we have the handling of the elements. All of those things compound so that when we finally get a film element or a magnetic element to start our restoration process, we have a series of artifacts that are embedded in that media that we have to deal with. And we have to peel back the onion and know how far to go and how to address those things. Here is, and we don't have the time today to belabor the specifics, but a table that shows you the kinds of artifacts that occur or are introduced at different stages. And in the column on the right, where you see the word common, right? These are the most frequently seen kinds of artifacts. And when you see the two asterisks, these are artifacts that can be introduced in multiple places. For example, jitter and weave, which has to do with the instability of the film, which has to do with perf tolerances and things like that, can have been introduced in the original photography. It can come in because of duplication, right? Dirt and scratches can really come in anywhere. So can flicker and color breathing. So remember that and grain is built up as well. You have the original photography and then grain that's introduced as you make duplicates of those elements. So when we see the imagery that we get to start our restoration project with, the grain we see, the flicker we see, the dirt and scratches we see, the instability we see, can have been part of the original or been introduced. And it turns out that that's important, because one of the challenges here in many restorations is to deliver something that's historically accurate, to replicate the visual experience the consumer had when the film or TV show was first introduced. And therefore, we want to peel away the things that came in with age and handling, but not go beyond what was actually in the original. And at the moment, that requires a human being to make the judgments. If our goal was only to maximize image quality, automation would be a much easier job than it is when we have to worry about only taking part of the artifacts that we see out of the imagery and having to essentially be driven by human judgments of how far to go and what we think the original conditions were. But this interplay between human judgment, human interaction, and technology is at the moment an essential and necessary part of restoration. I just wanted you to get a perspective for why those two are so tightly tied. If we look at an overall simplified look at restoration, there are essentially 4 steps. There's the automatic detection of artifacts, there's the replacement of those artifacts, and then there's that human review, which is to decide whether or not they were replaced well, whether they were all detected, whether the right things were fixed, etc. And then often there's manual retouching to either put back things that were removed and shouldn't have been, or to remove things that should have been detected but weren't. This is the simplified process that almost everyone in the world uses. Our goal here to get our costs down, to work down that pyramid, is to reduce human intervention. And if I go back here for just a second, the cost, the primary, the highest cost is in that manual retouching and human review. And the way to reduce that cost is to do a better and better job of detecting artifacts and replacing those artifacts. Those are the fundamental needs of a good technical system to drive our costs down. So we have to reduce this human intervention. And I just want to make one small point about this. It's not just about cost, all right? Lowering cost is why so much restoration has been done in countries with lower cost labor. But the reality is, even that doesn't drive costs low enough and make enough of a difference, because there's a limited number of really skilled imaging specialists, and there's so much media to save that we have to do something about project timelines, and just having to review these things with a human being and go in and retouch single frames makes it impractical to do the hundreds of thousands of titles that are out there. So automatic image processing must replace as much as humanly possible and take this manual intervention to a minimum. The underlying problems that technology has to deal with are what are called false positives and false negatives. That is, detecting something that it believes is an artifact and removing it when it shouldn't have been, or false negatives, which is not being able to detect an artifact that truly is one. For the sake of time, I'm not going to go into detail here, other than to say that the challenge in doing this detection right comes from kind of 3 places. One is complex motion. Remember that essentially what the computer is doing is saying, hey, since I know where everything is going on a frame, a moving image frame, and I can then decide what belongs and what doesn't belong, and I can get rid of the things that don't belong and replace them with what I thought should have belonged. All right. This is very tough as the motion gets more complex. Explosions, occlusions and disocclusions, things like that. And then you have 2 last issues, which are what I call single frame events, right? What happens when we have a scene with a dinner party and a woman's head turns, and on one frame, the light hits the diamond earring in her ear and glints, and it is a single frame event that's going to look to any algorithm like dirt and be removed because it can't have been predicted. And then there's scene content itself. What do you do when you have a snowstorm and there's white dirt? How do you tell the difference between different kinds of scene content? So Alex is going to address all of those kinds of things. Here is a quick summary. Again, we don't have the time today to belabor it, but this is going to be put up on the website. This really tells you where the state of technology is for different kinds of imaging algorithms. Largely speaking, there's been enormous progress made. And for the most common artifacts like dirt and scratches and image softening, as well as grain reduction to peel back the impact of copies of copies of copies. Tremendous progress has been made, but I don't want to steal any thunder. Alex will go into more detail now to take you through the technology path. And you're muted, Alex.
Unmute. Okay. Unmute myself. So again, thank you for the invitation to give this talk and to tell about our technology. By the way, if we talk about the previous slide, I think that probably 8 of 10 problems our software is trying to solve somehow with existing algorithms. Okay, I go. Can you see now PowerPoint?
Yes, but we're in speaker mode. We need presenter.
Yes,
presenter mode.
I need. It didn't show full screen yet, right?
No.
Now it's okay.
Yes. Please proceed.
Okay. So I'll start from a general principle of selection of neural networks for our purposes. Somehow, neural networks, which are developed by tens of thousands, I believe, people, if we are going to hire them for our job, they are like people. They have many common features, like layers, like loss functions. They have to process some data and output some results. Is just decisions which has to be made or create new content.
Excuse me, Alex, could you please speak a little louder?
Okay, I'll just
Thank you.
a little bit closer to microphone, I think. Okay, so there are 4 main cases how we select artificial network for our work. The best case scenario, if we have common task, we'll just pick up a state-of-the-art trained neural network, which usually has amazing property for standard, amazing quality for standard tasks. But unfortunately, in most of cases, especially for restoration work, it doesn't work well. Usually we have some specific data, at least some of specific data, and we need retraining. Retraining starting from the place where, say, classical neural network was trained. So we add our data and retrain a little bit. Again, not most typical case. More typical case when we need to take our data and retrain it completely. Moreover, usually we need to introduce some changes in a neural network, or even to create our own model from scratch. Usually it doesn't mean that we invent some special layers and some special neural networks. General architecture could be same as people doing with different problems. But anyway, usually we need to introduce some changes and use our data for training. I want to pay attention that find convergent algorithm for tuning network sometimes are very, very difficult. As Mike told you, it's 2 main problems. Roughly speaking, 2 main problems for film restoration. Identification that some object is defect, and second problem is creation of new content, so replacement of found defects. Legacy methods, which we used a lot, they mostly were based on applied harmonic analysis. We came from this area as mathematicians. We worked on this many years. And how harmonic analysis was applied it's for feature extraction. Feature extraction, this means that we take our data, analyze them, and give output, for example, a few features of the object. So what kind of systems for classical signal processing existed? Okay, of course, this is Fourier transform. Of course, this is a wavelet transform, Gabor transform, wavelet packet transform, and so on. Each new tool appeared not very often. Usually it's one for 10, 20 years. So very slow development. But if we have features and we have a very good tool for representation of data, we can extract a few features and apply classifier, which will give us solution, will give us decision, say for image recognition, is it this a car, or this is a cat, or this is a dog, or whatever, or this is a scratch or non-scratch in our case. And we worked in this many years, it means more than 10 years of development of different algorithms. We consider them as successful, but deep learning brought something new. First of all, these two steps, feature extraction and classification, were put in one box. So everything was going on simultaneously, feature extraction and classification. Somehow conditionally it can be separated, but essentially it's in one neural network. And what is important, that feature extraction system is found adaptively to our set of data, not to class of mathematical class of some objects, which could be sometimes a good description of a real world problem, sometimes not very good, sometimes it's approximation. But now we are able to use feature extraction adaptively turned, and so quality increased significantly. Okay, those two main problems, classification and generative neural network, or detect artifact or replace artifact, they're represented on two schemes. Both of them are more or less standard neural network consisting of convolutional layers, fully connected layers, different kind of introduction of nonlinearities and so on. But in the end, we have either some low dimensional output, mostly it's one number, say cat or dog, or we have output as another image, maybe not the same image, something, of course not same image. This scheme at the bottom shows approximate scheme how frame interpolation may work. Sometimes they work together and quite successfully. Again, it's I repeat, same neural network creating content, but below we have generative adversarial neural network. What is the difference? It consists of two neural networks. One is, in fact, it's called discriminator, but in fact it's classifier, and other is some neural network, which generative neural network generator of, say, images like here. But what is important that both of them, classifier and generator, are trained simultaneously. Discriminator has a set of actual right correct objects like right images, and generator is trying to create new images. Each new images is given to discriminator. Discriminator knows that this is a false one, and is trying to set the parameters to give answer that, okay, this is a false fake image. But this number, this output, degree of how bad images are sent back to generator. And generator tries to learn how to do better, and discriminator is trying to get fake images and give correct answers that this is really fake images. Finally, they are trained so well that images are produced perfect or almost perfect. It's a fantastic scheme. Unfortunately, it has some element of randomness. So for a restoration, it's a little bit scary to use it because it may create something new in one frame and doesn't create this new on other frame. And if you run video, it could be much easier to understand that this is some kind of fake sequence. Anyway, it's I think it's a big perspective for new neural network scheme. So how it usually works? We assemble a large and relevant database of good and bad samples. We collect them as training set. We choose architecture. We train neural network on our data. Then after tuning, we validate results. And then we implement this for our customers. This new implementation could be on different programming language on different platforms, so on. So it's quite separate, and it has absolutely different intention and problems for programming. But anyway, long training will bring us to fast computation of the trained system. Again, I repeat Mike's scheme. It shows in orange or yellow circles. It's our part to do automatically detect artifacts and replace them, and then human must check it and introduce manual retouch. The better we are, the less cost of film restoration. Okay, so a little bit more specific things about neural networks in our scheme. So what classification neural network usually are doing? How they do their classification? I'll show on simple scheme. You see on the left side blue and red points. You can think about them. One of them are scratches, other non-scratches, and we need to separate them in somehow non-linear way. What trained neural network is doing? Approximately what would human, very qualified human would do it. It takes this two-dimensional space, this plane, it's shown on two-dimensional space, put it in high dimensional space and in three-dimensional space. It's bent this plane, it becomes surface in 3D, and then we can separate it by a regular plane. Very simple. But how to do it analytically, it's very difficult to understand. But neural network training is doing it very efficiently. Moreover, it's not two-dimensional space. Say here I show vertical stripes. It's our training set. Some of rectangles contain scratches. You may see it. Some of it's marked by black. It's the down of rectangle, and yellow rectangles where no scratches. Sometimes they are very similar, but still different. Then we run, and this is, by the way, dimension of this is 512 by 32. It means that 15,000. It's not 2D input. It's 15,000 dimension of input. It's after a few layers of transformation, it does its work, and it does its work actually very well. How training goes? We just take training set and run it through neural network, which originally has random parameters. Of course, at the end we have some nonsense, but we know that this nonsense because this is annotized or labeled sequence of input data. We say, okay, no, you are not so good, and we send back signal, which is called gradient back propagation. We correct our coefficients a little bit, very little bit, and then we repeat our procedure. Probably it still will be good, but after 10,000 or maybe millions of steps, neural network becomes better and better, and finally we put those parameters, computed parameters, tuned parameters, into our real-world software, which already does its work very well. So how well? I'll show you an example of dust removal. It's actually difficult, very difficult for automatic dust correction, because here we have some small particle of dust marked manually with these green circles. Maybe you even do not see because they're small, but they were found because we know sequence. We can switch frames and see what is particle of ice and what are particle of dust. So green button. Our previous software, legacy software, did its work very well, but not in such cases. So the result is something like this. We see what green is correctly found and corrected. Now red one is false positive. So neural network software found and removed particles. Turned out they're not particles of dust and just particles, just objects from real film. And blue one not found particles of dust. So you see only couple of particles were found in good form. Now we run absolutely same with straight neural network, and you see here I see only one blue circle where very small particle was not found, but no false alarm, false positive. And this is fantastic. Of course, this is a very complicated thing for work in. So okay, this is the final result. In average film sequences, neural network has advantage about 30–50% better in both positive and negative. It's very approximate number. We didn't compute it accurately. It's just how it looks like. And this is pure economy of human work or price of restoration. How better this is. But actually, it's huge. Okay. Now about neural networks which create new content. So we have some input information. Maybe it's image and we need to get another image, say denoised. Maybe something else like optical flow computation. But how it works? We have some knowledge what has to be done at the end. And we have some maybe loss functions in one case. Maybe in better case it has to be generative adversarial network, which decides itself what is good, what is bad, which is very attractive. But having same information, we can get absolutely different output. And everything is about our knowledge. And knowledge mostly is based on statistics, on samples. And we need to create from information something visual now. So at least two-dimensional objects, pixel-wise objects. So when we can use it, first of all, of course, fixing large spots, large or small spots and splices on image, so some spoiled places. Of course, optical flow. Optical flow or motion estimation is main engine of film restoration. No optical flow, no restoration at all. Then we can do frame rate change, just insert intermediate frames in film sequence. We can fill gaps of missing frames. It's very useful because sometimes frames are damaged very much. They cannot be restored other way. The interlace also is new content between lines, which has to be installed. Upres or super resolution, again, new pixels. And two special cases, enhancement and grain generation. It's more or less about human judgment, what is enhancement, what is grain generation. But we are trying to suggest some tools with parameters which allow us to select the degree of this enhancement and improvement. Now, first, a little bit about generation of optical flow. What is optical flow? It's just field of vectors of displacement between frames. So output is something like image, but not image itself. So if you take images from amazing papers about new methods of optical flow computation with artificial neural networks, you will see something like this. It's pairs of image and optical flow. The color on optical flow part is just magnitude direction of optical flow vector. It looks really very good, much better than all previous methods based on PD, variational methods, and so on. Quite sophisticated methods. But artificial intelligence is much better, much stronger. What is bad about this? You see here cartoons. You can see in papers computer graphics for training optical flow neural networks. But in real life, in films, and especially in all archival films, quality of image is so bad. But even if it's good, it still has a lot of artifacts from the point of view of optical flow. For example, grain, even perfect grain introduce huge disturbance in computation of optical flow. Because original optical flow computed in computer graphics doesn't have noise, doesn't have flicker, doesn't have artifacts like scratches, dust, and so on. And as a result, standard neural networks absolutely cannot be applied at all to film restoration. This is a regular, more or less clean film, and if you look at it's already with our some kind of maybe intermediate our optical flow, you see sharp edges, which is very good. But on this image, everything else, okay, it looks very attractive. And two more pairs, again, it looks very attractive. But if you run the first sequence, look at here, fantastic edges. But you see, for example, scratch. I hope you can see scratch. And do you see the running video? Is it okay?
Yes, it's fine.
Yeah. So you see scratch, which is, of course, error in motion estimation. We don't need, we need motion of background. Instead of this, we see scratch, motion of scratch. This is even worse. You see background actually, generally it has to have absolutely same optical flow value. But what we see on the background, we see huge amount of artifacts. And actually those artifacts will bring to very bad things. For example, if sequences with flicker, then this means algorithm is trying to catch flicker as a moved objects, and it will compensate flicker and it will not remove flicker. Absolutely same about particle of dust. Even worse, such motion will introduce such behavior of processed grain that you will see moving grain, which is really disgusting. So it's necessary to do something, and methods of regularization to create some maybe a change of algorithm itself. And so a lot of problems around motion estimation. But this is what we have to do, because this is the main part of restoration. And we somehow did it. Okay, so one example of application of generative neural network is replacement of missed frames. Well, it could be more examples, and I'll show. But first example is about frame interpolation. We have the first frame good and the 9th frame good. In the middle is something which I cannot use. I need to generate those frames. I'll show this sequence. This sequence. On the left side is original. On the right side, I'll show video. You see on the left like flicker. Actually, Viva is working with flicker very well. But Okay, why I cannot run it again? The point is that the nature of these images are very specific. This is the first film of Technicolor created in 3-stripe technology. And after they created this, they finally put everything on 2-stripe tapes, and they do not have entire set of frames in 3-color. And here we try to just reconstruct 7 intermediate frames between 2 good 3-color phrases. I'll show what's going on. I'll show it in blue channel of the picture. The first picture is good. So you see left side, right side, it's absolutely the same. Original and processed. But all other 7 frames, I show you the 5th frames. You see blue color is absolutely different. Look at head, for example, bend of the head. It's in fact black on the left and light on the right. This is because the left side was reconstructed from 2 stripes and right side is from 3 stripes. So we needed just to replace. It's not flicker, it's much more severe damage. Okay, and this is again the last one is good. Now I'll show you a few samples of frame rate conversion. Unfortunately, you probably will not see it in good quality because now it's 48 frames per second from original 24. But let's see. So it's very complicated just because a lot of small details. But at least what you probably can see or cannot see, probably you cannot see artifacts of intermediate frames. You may maybe see not all 48 frames per second, maybe some of them randomly. But at least we think that it looks quite good. Okay. It's very complex motion here. Very complicated occlusions, especially difficult close up. Okay, and another application of generative neural network for restoration is press or super resolution. This is a low resolution image. This is what is traditionally used before AI. This is a bicubic interpolation of pixels. This is a double increase of resolution. And this is what artificial neural network can do. Just again, I'm not sure that quality on your side will be very high after this transmission, but you can compare edges. You probably will see difference. Another low resolution input, bicubic, and then AI. Bicubic, AI. Pay attention on shoes, on rails. Okay, this is very shortly. The interlace is a very important problem even for film restoration because in many cases people scanned films on old telecine technology and then lost originals. It needs to be reconstructed. Also, this is about generative neural networks. This is enhancement, including some sharpening. Also, what Viva can do. This is a few frames from a couple of frames from Scarface 1932. It was restored in 2017 by Universal. It's film by Universal. And what is difficult here, on the left side is tens of scratches. Actually, viewer shows that it's about 100 scratches per frame. Most of them are hardly visible here. And very low resolution. People who restored it, it was MTI, they accepted that actually, while it was 4K scanning, actual resolution is about SD, standard definition. Okay, again, back to original. And so if you do not see details, I'll use some zoom of pieces. This is those scratches. Pay your attention that grain here, in spite of sharpening, grain stays absolutely same with no change. I'll give you comments a little bit later about this, but now just pay your attention, because it's not big deal to increase sharpness, but in such situation it will increase grain magnitude, which may look disgusting after all. Okay, and a couple of more examples of enhancement. Okay, and again, to the problem of the grain in particular, more about our main brick of our technology. Technology is based on one pass, mostly on one pass processing, which includes everything: stabilization, superfilter, which is the grain and the flicker, so that special and temporary artifacts, dust removal, deep enhancement inside, and then we return flicker back if necessary. Sometimes I can tell you even flicker necessary to be removed. For example, if you restore, say, rock concert footage, all this flicker is natural part of film. And then you return clean grain back. So why this is good? Why this is a very good? First of all, of course, the most visible part is that it's faster, because it's still not fast, but it's much faster, because we put everything in one mode. Second, all those modes, they have exchange of parameters and help each other. So from this point of view, quality is better. But the most important part here lies in the line superfilter, the grain and the flicker, and then return grain back. Why this is important? Because when we remove grain, we remove noise, whatever, we remove everything from this special spectrum. We still have dust, but dust is clean, and grain is not an obstacle for removal of dust. Dust is removed from smooth surface, from smooth background. Enhancement, again, we can improve edges, we can improve details, but we will not magnify grain. And these two parts, pay your attention on this, and then everything is inside. So we remove dust, and then we apply enhancement, and then we return whatever we need back. And this gives huge advantage. We have absolutely natural grain. Grain is a holy cow for archivists, for many people who deals with films. So grain has to be preserved as much as possible. Okay, now, Jeff, could you please run a couple of clips from your side?
Sure.
Okay, this is a paper print, actually not even actual movie. It's a movie was created in 1903, and simultaneously it was put on photo paper. It's the known patent by Thomas Edison for two purposes: probably for preservation, and second, for preserving copyright, because at that time copyright existed only on images on photo paper, and Thomas Edison tried to save his right in all possible ways. So this material from Library of Congress, only recently it could scanned, and then it was processed. It contains all problems of film, actually grain and very high level of grain, but in additional problems of artifacts. Also scratches, of course, from film. Of course, in many cases, paper prints just replaced non-existing original films. It's big collection in Library of Congress and some other places. Okay, please next. The previous footage, I don't remember, did I say that's 1903 or 1905? It's from different sources, different data. Okay, this is The Loves of Carmen. It's a film from MoMA. It was recently restored by Image Protection Services. It has a lot of flicker, a lot of vertical scratches for other artifacts, and this is automatic processing. Again, of course, you see overcompressed film here. As original is much, originally restored is much nicer. Okay, thank you. So again, the main idea of technology is to put together all old known ideas of computational harmonic analysis, combine it with AI. Currently, it's about 80% of algorithms based on AI, maybe 20% are based on regular algorithms. But combo filter construction all in one allows to create some kind of miracle, because it's really preserve what people want to preserve, and it's remove most of artifacts. So everything is implemented on GPU, so it requires a lot of course computational energy, but it works.
Terrific. Well, thanks, Alex. That was really terrific. And I'm going to go off script here for just a second. Can everybody hear me okay? Just wanted to
Go ahead.
All right. Yep. I want to loop back and just grab two thoughts that that Alex put out there, because they're so important, and we delivered so many other things. I want you to understand how important they are. Those interpolated generative images. Take, for example, the avatar sequence. If you were able to see the footage in full resolution, what you'd see is that every in-between frame, which is being computed in an extremely complex motion situation with noise, right, has been created artifact-free and seamlessly fits into the sequence. And what that means is, if we can detect artifacts, we have the full palette of what to replace them with, because we're able to compute these frames extremely well now. And that is a cornerstone piece to making restoration more affordable. It's also important because, as I mentioned earlier, as we get to higher and higher brightness displays, and as we move to higher frame rate display, we have virtually all of our legacy media out there shot at 24, 30, 29.97, 25, and then older films even slower. And we're going to have to do something about that to allow them to play effectively on these new devices. So that's a really seminal piece of technology. And so is this issue of very high quality de-interlacing and up-res. Even if you just look at this from the perspective of all of the home movies, whether they be 8mm, 16mm, VHS or otherwise, that you now want to look on your view on your 62-inch high dynamic range television, right? This combination of de-interlacing, up-res, and enhancement is a really important part of keeping them relevant to people who might otherwise discard them because of quality. So with that caveat, on to some concluding thoughts. First of all, a quote from Kai-Fu. He's the chairman and CEO of Cinovation Ventures. He was a senior executive at Apple and Google and Microsoft. He's one of the kind of world-renowned AI specialists. And one of the points he makes, which I think is extremely strong, is that the real progress, I'll let you read the quote itself, the real progress we made in AI has less to do with new algorithmic ideas and much more to do with having enough data to train networks on and cheap enough and enough computing power to really make those things work. And so the first thing I'd like to put in front of you to think about is that for us to continue to drive the cost of restoration down, we've got to be able to recognize and correctly detect more and more artifacts with higher and higher accuracy. And we are at very high accuracy now with things like dirt and scratches, right? But there are many others. And we need access to a wide array of categorized samples. You don't have to have, remember, this is just about detection. You don't have to have the fixed version. We just need to know this has the artifact and this doesn't. We're seeing this a lot from Asia, for example. We're starting to see more and more footage with mold in it, which is a very invasive and tricky imaging problem because it organically grows into the emulsion. But all of these kinds of artifacts, different kinds of artifacts, the more examples we have of it, the better we can train the algorithms, better we can train the networks. So access to samples and access to computing power is what's going to help us drive this technology across the finish line. So if you can think of ways we can collaborate and share this information, that's really key. And by the way, if you remember the slide Alex put up where he talked about the training samples for scratches and that they were, I think you said, Alex, 512 by 30. Or in other words, they were little snippets, right? They were not the full images. So for those people who deal with intellectual property problems and ownership, the training samples do not have to be full images, which means there may be ways to expand this training set without running into other kinds of problems. So I wanted to hold that one out, number one. Number two, remember that the restoration process we're talking about, its downside or its most significant cost is human intervention and manual retouching. But it turns out, interestingly enough, that the work we do in human review and manual retouching can help us make AI better in the short term. So we believe there's a collaborative machine learning model where people who are actually doing restoration projects and have the experience of footage which I'll say fails, right? They're put through the artificial intelligence algorithm and something's been removed that shouldn't be, or something's been left behind that should have been removed. If you have to go in and retouch it, that information, just the fact that you're saying what was done here should have been done like this, can be fed back and used to improve the algorithms. So we believe there are ways to collaborate on using this information of when labor was required to improve the algorithms. And again, we would love to discuss ideas in which this can happen, because big picture here, we're trying to save the world's cultural, historical, scientific, entertainment assets before it's too late. And this information, along with a training set, can help us get there. Lastly, the restoration market is funded only by commercial return in most cases, at least for the entertainment assets. But the problems we need to solve overlap with the problems that the scientific and medical and educational and consumer, especially consumer photography and videography worlds need, right? The things we're trying to do with noise reduction and detail extraction enhancement, those problems overlap. So to the extent you have relationships in, or you work in those spaces, and there is a way to share on the technology side to help raise the bar for everyone, this would really be helpful. I don't think very many people jump into the restoration world to become wealthy, right? It is because of our love of the underlying value of what's in this marketplace, and we need to beg, borrow, and steal. And the reality, I'm using steal very loosely, I really mean beg and borrow. Any way we can collaborate here would be really, really helpful. So those are the three thoughts we all wanted to leave you with. Special thanks to Louise and Lauren, both for inviting us here and for working so hard on helping us get this presentation so that hopefully it was useful to you, and to Image Protection Services, MoMA, NBC Universal, Technicolor, and to all of you. This is about access to the materials as well as for your attention today. So thank you so very much. From here, we'll throw it to you to ask whatever questions make sense.
By the way, we
Thank
did
you very much.
Library of Congress.
Oh, and Library of Congress. Thank you.
Okay. So we're going to drop screen sharing. There we go. Hello, everyone. Thank you so much to Mike and Alec for the in-depth presentation. And I'd like to throw the floor open for questions. I don't know who wants to go first. There are a lot of people here that know a lot. Who would like to just wave and we'll just.
I'll go first.
Okay. Hi, Louise. Okay.
Hi. It's a question for Mike, and obviously based on your presentation, there are lots of moving parts, but I'm curious if you can, what I'd like to know is what you think the most important problem there is to solve in order to really make an impact on saving media assets that are really in jeopardy.
Sure. My opinion, I guess, is this. It actually falls outside of what we've talked about today. So, and let me see if I can explain this in layers. As we discussed, the media is losing quality every day. Mm-hmm. And in the case of the magnetic world, the players are becoming fewer and fewer and less accessible. There has been a remarkable evolution of film scanning technology, right? The fact of the matter is that if we can digitize these assets and get them stored, understanding that digitization is probably not going to get much cheaper, right? Storage is already pretty inexpensive. It's going to continue to get cheaper, right? And the processing, as amazing as a job as we've done, the processing is going to continue to get better. right? Even if all you do is scan an asset and put it away for 10 years to come back and see where Alex and Ina are circa 2031, right?
Uh-huh.
Right? Where the movie is actually returned to you before you submit it using the new miracles of AI, right? And they're able to remove 99.99% of the problems instead of 98.5 where we are today, right? You will have stopped that degradation as long as you do the digitization and you have a migration strategy for the storage.
Mhm.
And as long as you've asked me to answer the question, a pet issue is, I think we have, there isn't much further we can take film scanning other than to do it, right? And it can't get much more efficient because you can't move this film faster without putting it at risk. We're already getting a great bit depth and great resolution, et cetera. That is not true of magnetics. Our approach in the magnetics world has largely been to try and keep some legacy machines still running, right? And the things that we do in the film world, we are arguably digitizing with smaller pixels,
Mhm.
right? Substantially smaller pixels than the smallest grain on the film, which represents the maximum kind of resolution that's there. In the video world, we're using the same old clunky heads, right? That
Mhm.
were used to record this stuff, and we're not in technical terms oversampling anything.
Right.
And we're dealing with magnetic media that has NTSC subcarrier artifacts and other things associated with it because of how it was put down. And we could build devices that are faster and similarly extremely high quality for the magnetics world. There was a startup that tried to do this, which I don't think got very far. But for the world, with the amount of magnetic media out there, and the fact that magnetic media is falling off even faster than film media,
Physically falling off.
if I could wave a magic wand, it would be around getting things digitized and put into storage, and then getting them through something like Viva, which is best in class in terms of these algorithms and use of artificial intelligence, as fast as possible. But if that part has to be delayed a couple of years because of budgets, that's better than letting the media become unsalvageable.
Right. Thanks.
Thanks, Mike. Thanks, Louise. Great question. Who wants to ask the next question? Jeff Wheatley.
Yeah, so in this is a question for Dr. Petukhov. In your example, you gave some where you had a good frame and then a series of bad frames and then another good frame. What, so I've done some of this myself, and what I found was it was really hard to maintain spatial temporal coherence over more than just a few frames without keyframes. Do you use a generative adversarial network there, or what's your strategy for those long sequences? And then a follow-up question is, what's the longest gap you think you can fill successfully?
Oh, good question. Of course, number of frames, it depends on motion and only on motion for any algorithm. So you saw 7 interpolatory frames, and this is the maximum which is allowed in Viva. It happens same number. I didn't try to do more. If you ask me whether 7 frames always can be created, well, no, of course no. For more complex motion with more occlusions, probably not. So yeah.
Is it basically based on how far the delta in optical flow is for any given sample?
Yes, actually. If you can create good middle frame, then you can create everything else as well.
Right, you fill in the gaps, yeah.
Because it works actually in that way. It created middle frame or what is close to middle, and then created everything else using middle frame as reference frame.
Well, as someone who is interested in using AI and generative adversarial networks in the creation of art, it might be very interesting to purposefully misdirect that tool and see what you get.
But for adversarial network, it's my just thought that they create fantastic results, visual results. But what about video? I don't know. I didn't see good results, because if it works on separate frames, it's probably because of randomness of some details, it will not work. But if it works on sequence, probably it's prohibitive complex systems for training. At least I didn't try. I'm still waiting for.
Yeah, and I haven't seen SIGGRAPH papers or other papers that address this problem either. They're surely coming. For me, I find sometimes it interesting just in the images that the GANs generate, not from a restoration perspective, but just as images themselves.
Enhancement. Yeah.
All
It's
right.
really-
Thank you, Jeff. And I'm sorry you didn't have the first question, Jeff, in your traditional spot, but it was still a really good one.
I have a new role here in the community forum, so.
For those who don't know, Jeff, in the live CineGrid workshops, Jeff always had the first question. Who wants to ask the next question? Yes, sir. Joseph Mark. And you're muted. There you go, Joseph. Thank you.
I didn't know if the mute was yours or mine. Okay. When you were describing in the presentation, if the goal is visual quality, then you can use the science and the neural network tools you described, plus automation. And I'm wondering if by automation, do you mean something as simple as a watch folder or right click on a folder and process all the images? Or are you thinking more in terms of like a dashboard or a workflow or tool tips or something that helps someone get a work done?
And who wants to take that, Alex or Mike?
It's a question for me, of course.
Very good.
Actually, automation means full automation and all possible intermediate stuff as well. About full automation, we have, I don't know, 10 presets. Studios, I mean, for professional restoration, unfortunately, people use 2-3 presets. So those 2-3 presets definitely they good for one reel of film. So just push a button and it goes. After all, of course, it's necessary to have control. It's necessary to maybe some manual retouch, but we are trying to reach good quality with no false alarm and no errors. Of course, it's impossible, but just the amount of it. So this is a full automation in this sense. There is option which is called green button. And to our knowledge, maybe 60% of our clients, again, unfortunately, they use this green button because Viva has much more power to do much better work. But for most of customers, including high-profile customers, usually even green button is good. So difference is what they use. Okay, green button say it doesn't remove very fat vertical scratches. So there is special mode which allows preliminary to remove those fat scratches. Or this is a 3-color separation. So dust appears only in one channel. Okay, different algorithm is used. Of course, it's better to take this knowledge. But generally, It's very, very pity that semi-manual work for tuning presets. Usually, it's good, but it's sad because we know that Viva can do even better.
And Joseph, did that answer your question?
It did, but it kind of pointed to something that Mike said when he did that pyramid of, because, we just answered for a single title, as he said. But Mike said in the pyramid, 10% of the value is in the culture, heritage, scientific, military, and so on. The numbers of films are much larger than Hollywood ever made, right? So the automation to scale for those people will have even more impact, but even less human possibility to.
Right. Yeah, it's, if I may, and I've actually got, well, go ahead, sorry, Joseph.
No, I wasn't trying to ask you a question per se. I wanted to tee you up because I want to hear what you think.
Sure. Well, and I'm actually going to break the rules and ask Alex a question at the end. So, number one, there's kind of a ethical cultural issue here, right? Which is that we're being driven by, largely we've been driven so far by consumer return, right? When you would hope that governments, for example, would spend tax monies on restoring historically critical, footage, et cetera. So there is a funding, element to this. And I also do think that making it available and searchable, et cetera, can generate a source of revenue, but still you have the problem of the base of the pyramid. I wonder, and this is my question to Alex, and then Joseph will loop back in case we didn't catch you. So you mentioned that you have kind of 10 presets, right? But people use too few, largely because it's simpler to do so. I'm wondering whether you think would be possible technically in the future to pre-scan the reel, for example, to determine this is a high grain sequence. It is clearly 3-strip because of what's going on in the red channel, which tells us this is 3-strip. It doesn't have scratches, but it does have and it has simple motion. So we can use aggressive preset 2B, right? And that's automated by essentially pure measurement, if you will, or whether you think human decision has to be part of that.
I think it's not only possible, but maybe even not very complicated. Of course, it takes something, it's something new, but it can be done for sure. Only one thing which cannot be defined automatically. The point is that we have, say, 3 presets. One is called mild, one is called confident, and one is called green button. Green button gives visually much better results. But mild, say, it's more responsible. It will not remove some suspicious dust, which when algorithm is not quite sure. And for professional restoration, they prefer to have guarantees that nothing will be removed by mistake. But for people who want to have instant result, high quality result, green button is better. So how we can decide by footage? It's human choice.
And we have another question from Todd Margolis.
Hey there, thanks for a great presentation. I'm wondering if, especially, for maybe the more professional work that you do, if you use multiple, if you train custom models, potentially, like, I'm thinking like by director who has a particular aesthetic, or even by like the type of equipment that is used, or by genre, or by indoor versus outdoor. If you have any of these kind of custom models that you're training for each type of project.
Yeah, it could be great to do this, but where data are? How to find those data is not acceptable for training. It's the critical stuff. Restoration. So, and by the way, it's a scheme which Mike showed to you in the end for collaborative tuning of neural networks. It can work in 2 modes. One mode, everybody sent automatically the result of their manual retouch or manual corrections, and then neural network is trained average. And other mode, which can be implemented even maybe on customer computer, when someone starts working, only this data, say someone starts working, process a few scenes, few shots from film, and this result of this work goes to some kind of for extra tuning. Then it may take this data about some specific test, specific desires, what has to be done. Maybe more dust has to be removed, even if with probability of some extra mistakes, maybe less, but to preserve from artifacts for lost details. Okay, so it can be done in architecture, which we discussed in the talk.
Got you covered, Tom?
So what was that?
Did
I
we
was just-
cover? Go ahead, Mike.
I was just going to add one short piece. This is a little askew from restoration, but when we introduced the Cineon digital film system, which introduced 4K and digitization, et cetera, back in 1992, among the first people we went to, because we were Kodak, right, was the cinematographers. And one of the things they wanted, I wouldn't classify this as restoration, is essentially custom looks. And the ability for, you can imagine, what would it be like if I shot, and there are directors working on this now as well, shot flat, full depth of field imagery, right? And then said, make this look like Scorsese shot it, right? Give this a 1920s look, et cetera. And you had a set of presets. Now, again, this isn't about how you remove the artifacts. It is about, the image structure, the tone scale, et cetera. But all those things are absolutely possible. And it starts getting really interesting as you move into that creative side.
Right, that same model could be used for image transfer or for restoration. Yeah.
And I would say we had in Angus Forbes' talk this summer, he talked about people applying styles, and it was similar to what your style transfer. I'm getting a text from over the chat. So that's a very interesting. I want to make sure that people who want to ask questions get a chance. So thanks so much, Todd. And anybody else want to jump in here?
I have a question.
Sure.
It was mentioned that you're interested in having access to material that have defects. If I understand, are you saying that you're interested in having access to things that have already been scanned, or things like just the physical objects before they get scanned? Because I'm thinking, don't you think you could maybe partner with Film Archive locally? Well, I don't know where you are, but in LA, we have UCLA Film Archive. They have so many things. I think they have a scanner, but they have to use it to mainly, I believe, scan newsreel material that they have. And the main reason they have the scanner is because of philanthropists, help with that. So the archives are very underfunded. But don't you think maybe you could partner with a film archive that gets a grant specifically to help fund this type of research you're doing, and then you will have all the materials from the archive?
Yes, I think it's an interesting direction. I think that from a practical standpoint, because some of these problems are fairly fully solved already, right? We don't want another, 500,000 cans of material with dirt, right? However, if it comes to mold, right? If it comes to unique kinds of flicker, and we can look, I think it probably falls on us to be more specific, right? And then what we really would want to be saying, and this is something we could do through EMEA and other places, is to say, if you run into these artifacts, please contact us once you've digitized them, because we don't have a digitizing operation, right? And what we'd love to do is is train, train the algorithms to do a solid result. And in the end, you'll get a better result as you continue on through the restoration process.
And did we cover your question, Alexandra?
Yeah, I had another question.
Go ahead.
You said that it's true, it's a race against time, no? And but there's different types of scanners, and I'm not an expert, but I believe some can introduce some type of even processing as they do scan the image. My question is, if you in an ideal world for you, what do you think 10 years, let's say 10 years from now, I scan something today, and 10 years from now you have, whoa, I'm ready to look at your scans from 10 years ago. What do you think should be the best practice, no, for the client to engage, to tell the vendor that is going to do the scanning, to make sure that we have the best available scanning for you 10 years from now? What is it that we should tell? Don't introduce, maybe don't do processing, or don't do, what would you tell somebody to consider?
Sure. Well, I guess I would use two things as examples, right? For example, there are a number of scanners now that use infrared technology to try to find surface dirt that's on the film, right? To be able to detect that there's dirt there. And ideally, we want the dirt map that says, here's where the dirt is, and not the footage that the scanner has processed to replace the dirt, because what they can compute in real time as they're scanning, and frankly, their expertise is not the image processing, right? So they will, generally speaking, and I don't mean to disparage it, I'm not trying to speak negatively, they won't do anywhere near as good a job at concealing that dirt as we will, right? But if they tell us where the dirt is, right, that job's done, that's wonderful. The same thing is true that, every scanner, when you get into the physics of how it operates, it's got the problem of uniform illumination. It's got the problem of uniform sensitivity of the sensor and its pixels. It's got the issue of bad pixels, which it has to replace, etc. And then it's got the quality of the optics. And as people drive for cheaper and cheaper scanners, they use less and less perfect lenses, right? And so then what they do to make the scanner look better is they add sharpening and other processing. So I would love to see some of that turned off, because again, what they can implement in real time as they're zipping the film through is nowhere near as good as the kind of sharpening and enhancement Alex is talking about. So I would have it be as clean as possible. Now, if they need the results now and they can't afford any other solution, they're going to run it that way. But I prefer as raw a scan as possible that deals with the scanner signature, but not the other pervasive issues.
It'd also be nice to have a markup of the scanner metadata, so you know exactly what it was, what the settings were, what the lenses were, the light sources, all that stuff.
Yep.
Thank you. I really appreciate wonderful answers. Thank you.
Sure.
All right. And so everyone, I'm going to thank our speakers. It's 11 after the hour, and I really appreciate both the speakers, Mike and Alex. Thank you for a really excellent presentation. And I want to thank our very good questionnaires to ask good questions. We'll be back, if you want to do this again, we'll be back again tomorrow at 10:30 a.m. Pacific Daylight Time. And we'll have the same content, and we'll have more question and answers. I want to thank, we will post this recorded session in a few days, and we'll send out a notice when that's ready, but it'll be on the CineGrid YouTube channel. And we'll also be posting the slides that Algosoft presented today. Really informative and educational. We had a lot of comments from people on the chat. Mike and Alec thanking us for the presentation. They had to leave at 6 o'clock. And so everyone, thank you, and have a nice rest of your day.